Welcome back to this unit on thermodynamics, and this is lecture 5 in this unit. So, in the first 4 lecture we have gone through the introductory part, definitions, essential definitions, and heat, work and energy, internal energy. Then we talked about first law of thermodynamics. We went through in details about calculations of work, heat in different processes, especially for an ideal gas, and we also talked about enthalpy and heat capacity in last lecture, and then we also found out or learned how we can experimentally measure delta U and delta H in a process, especially in a chemical reaction. Then we started about finding out del H, the enthalpy change in a process, mainly in chemical reactions. And if we can go back and just recap the enthalpy of reaction, what we have found out in last class. Remember, we talked about enthalpy of reaction, which is given by delta R H naught, and T means that particular temperature, which is given by A I H m naught at T minus B I H m naught T. A I and B I are the stoichiometric coefficients for products and reactants in their balanced chemical equation, and H m naughts are the standard molar heat capacity for each substances. Now, if we do not mention, generally if sometimes the temperature is not mentioned, then we consider the conventional temperature considered as 25 degree centigrade or 298.15 K. So, if we just write delta R H naught as I A I A minus B I H m naught, then you will understand that it means that we are talking about the reactants and products are there in standard state, and this change is happening at 25 degree centigrade. Now, we talked about just started discussing about standard heat of formation, or we call standard enthalpy of formation. Now, you notice that this standard heat of formation and enthalpy, these two terms are very frequently used interchangeably. So, you can either call standard heat of formation, enthalpy of formation, or standard heat of reaction or enthalpy of reaction. So, heat and enthalpy are very basically they are used synonymously in this case. So, you can tell any of these two quantities, and this definition required because as we discussed in last lecture that we cannot experimentally determine this molar heat capacity, molar enthalpies, sorry, I said heat capacity, it is molar enthalpies. Now, we cannot calculate the molar enthalpies because as we discussed earlier. Hence, we require the indirect method to find out the reaction standard heat of reaction or standard enthalpy of reaction, and that is the reason we define this term. standard heat of formation or standard heat of reaction, and we represent this as this for a particular temperature, and if I just write like this, then you will understand this is for 25 degree centigrade. Now, we defined heat of formation in last lecture. Standard heat of formation was, it is for a pure substance at a specified temperature T, is the heat of reaction or enthalpy reaction for the process or the reaction in which 1 mole, remember 1 mole of substance in its standard state at temperature T is formed from the corresponding separated element again at that particular temperature T, and each being its in reference state or reference form or reference phase. This is what we defined at the end of last lecture, and we also mentioned what is a reference state or phase or whatever form is the most stable state of the element at 1 bar pressure and that particular specified temperature T, and if we do as again if you do not mention T, then it would be a at 25 degree centigrade. And as you can see, we have defined it for 1 mole of substance, which means that it is a intensive quantity, it is always for 1 mole of substance. What are the standard reference state example? So, we can reference states for some common substances at 25 degree centigrade. So, dihydrogen is hydrogen gas, similarly dioxygen is oxygen gas, carbon is carbon in graphite form with at 25 degree centigrade 1 bar pressure. Graphite is the stable form of carbon. Similarly, sulfur in rhombic phase. So, these are the examples where reference state means is the most stable state for that particular element at 1 bar pressure and the specified temperature. In this case, we are talking about temperature as 25 degree centigrade. So, you give you example some of the how to get this enthalpy of formation or standard heat of formation. So, if we talk about for water, so standard heat of formation of water H2O liquid, then we have to find out the standard enthalpy of reaction or heat of reaction. If we want to get it at 298 K, then we have to get it at 298 K. What is the product? Product would be H2O 1 mole at standard state at 298 K. Standard state means, as we have described or defined in last class, it is for pure solid and liquid, it is the state which has 1 bar, if you can remember, and that particular temperature for the pure substance, and reactants would be from the elements from which it is formed. So, elements are oxygen and hydrogen in this case, and at the same standard states 1 bar and 298 K, most stable state is for hydrogen is hydrogen gas, and for oxygen this oxygen gas. So, it would be in 1 bar 298 K. So, these are the reactants as per our definition of standard heat of formation, and this will be your product. So, the reaction would be H2O gas plus half O2 giving rise to H2L. These are all at 1 bar pressure, standard pressure 298 K. And the value for heat of reaction for this particular reaction, which is equals to our according to our definition of water at 298 K is minus 286 kilojoule per mole. So, this is you can find out where we are the enthalpy or heat of formation of a substance is the heat of reaction of formation of that particular substance from its constituent elements, which are at their reference state and in standard condition, and reference state is the most stable state at that particular temperature and pressure. We can talk about other example. If this is we talked about H2O, we can talk about methane CH4 quickly. So, in this case the elements are carbon and hydrogen. So, most stable is graphite plus 2 hydrogen gas and CH4 gas. So, the heat of reaction for this reaction at 298 K would be equal to minus 74.8 kilojoule per mole. Hence, delta F formation of CH4 at 298 K would be same minus 74.8 kilojoule per mole. If we talk about other examples, C2H5OH, ethyl alcohol, again the constituent elements are carbon, hydrogen and oxygen. So, we can write a balance equation for 1 mole of ethanol, graphite plus 3 H2O gas plus half O2 giving us C2H5. Now, this is all we are talking about 1 mole. So, in this case 1 mole of methanol, 1 mole of ethyl alcohol. So, delta R for this or reaction enthalpy of this particular reaction would be equals to this for C2H5, then enthalpy of formation of ethanol, and the value is kilojoule per mole. So, this is how we found we can define the reaction the heat of formation or enthalpy of formation. One more example, if you want to get HBr gas, the enthalpy of formation. Now, the constituent elements are bromine and hydrogen. Now, at 25 degree centigrade, if you consider 25 degree centigrade, we want to find heat of formation at 25 degree centigrade. Now, at 25 degree centigrade, 1 bar pressure, bromine's most stable form is bromine liquid. So, we have to for heat of formation we can write this reaction. So, it will be half of this HBr. If you just for example, which is not a enthalpy of formation, for example, calcium carbonate we can form from by this equation. Solid calcium carbonate, but in this case the delta R, the reaction enthalpy for this reaction is not equal to the formation of CaCO3 solid, because in this case calcium carbonate solid is not formed from the constituent elements. So, remember the heat of formation, it has to come from the elements. Now, the heat of formation of an element in its reference state is taken as 0. Because no standards, it is the same reaction, like if I want to take the delta H formation of graphite. Now, graphite is from reference state is C graphite. So, the delta H formation for graphite would be the heat of reaction for this particular reaction at 1 bar and this particular temperature, but this is always delta R for this reaction is 0, which means that we can always consider that delta F for any elements at their reference state is always 0. Now, we defined delta H reaction as summation of H m 0 of products minus H m 0 of the reactants. I am not writing the term products and reactant, because we have discussed this earlier. Now, to make it simpler, we can just write a equation like A plus B B, just a simpler reaction. Now, A, B, C, D are stoichiometric coefficients. Now, I can make a cycle, like I can consider the reactants, in this case A plus B B in their standard state at some temperature T to products. Obviously, we are talking about this reaction, so which is C plus D again in their corresponding standard states and at temperature T. So, this is our reaction for which we want to get the reaction enthalpy or delta H R. We mark this number 1, equation number 1. Now, we can take it back, we can divide into 2 steps. First step, we are taking back to their constituent elements in their reference state at that particular state at that particular temperature, and from here we go back to the product, because the constituent elements for the reactants are and product has to be same. So, we can think or imagine that another reaction where constituent elements are forming the product. So, we mark them as equation number 2 and this is 3. Because delta H is a state function or state does not depend on path. So, we can consider the delta H R for first reaction number 1 is equal to delta R H for reaction number 2 plus delta R H for reaction number 3. We can consider because del H does not depend on the path. Now, what is reaction number? We can find out these two for the second reaction and third reaction. What is second reaction? All the reactants going to the constituent elements, which is basically the reverse reaction of formation reaction, and in this case 3 from constituent element to the products, which is basically a formation reaction. So, we can write the second reaction minus so this is delta R H 0 for second reaction 2 and this is delta R H 0 for third reaction. Now, this is the reverse of the formation reaction. So, we are putting minus sign, we can write this is formation of A moles of, because this is for 1 mole and we are dealing with A moles in this case. In this reaction we are dealing with A moles of A, B moles of B, C moles of C and D moles of D, and delta H or heat of formation is for 1 mole. So, we have to multiply by the number of moles here. So, we are writing B, and for the third reaction we can similarly write these are all at same temperature, okay, that is given. So, now onwards I probably will not write the temperature thing going forward, which means I can write del H 0 for reaction 1 as del R H 0 2 plus del R H 0 3, which is C del F. I am writing this first because it is positive sign. Which is nothing but as a general we can write the heat of reaction for any reaction would be given by summation of A I H I for the products minus B I at particular temperature at temperature T. So, if you compare that with the original definition of heat of reaction. So, in this case we are instead of molar enthalpy, standard molar enthalpy, we can write, we can exchange this standard molar enthalpy as the standard heat of formation for that particular reactants or products. I can give you example like we can talk about this reaction burn combustion of methane. You can compare a particular temperature and all are in standard state, then the heat of reaction or enthalpy of this reaction can be obtained from the enthalpy of formation for these products and reactants. So, we can write for the products first delta F H 0 of carbon dioxide gas plus delta F H 0 of H2 L 2 moles. So, we have to put 2 here minus delta F H 0 CH 4 gas minus delta F H 0 O2 gas 2 here because of 2 moles here. Now, this is the oxygen as the reference state at 298. So, this term the enthalpy of formation would be 0. So, if you know these values, then we will be able to find out the reaction enthalpy of this particular reactions. So, from this table these values are obtained from thermodynamic tables. So, we can get this number. I am omitting the units just to make it faster. 1 mole plus 2 ice into 285.8 minus 74.8, this is 0, which will give us 890.4 kilojoule per mole. So, this means that we can get the enthalpy of reaction or heat of reaction for any particular reaction if we know the enthalpy of formation of the reactants and products. Now, these equations where we write the balanced equation along with the delta RH values, we call this as thermochemical equation, and this thermodynamics which deals with the chemical reactions and the heat change along with that we call this branch of subject we call often thermochemistry. Now, for in this balance equation we have to mention the physical state of the reactants and products, and if it is in a particular allotropic state also we have to mention. So, these we have to take care in the balanced equation. Just for giving one example of thermochemical equation, we have just written in last example where we are giving the physical state of each reactants and each product. Now, in this case we are also giving the value for the enthalpy of reaction. It is better to write what temperature it is, 890.4 kilojoule per mole. So, this entire thing is mentioned as thermochemical reaction, and there are few things you should remember or keep it in mind about this thermochemical reaction and the property of delta H reaction. First of this number, this stoichiometric coefficients, this few things to remember, three things to remember. One, about three things to remember about these thermochemical reactions equations. One is this stoichiometric number or coefficients. They represents number of moles, not number of molecules. So, please be careful, it is not the number of moles, that is why it is always we can write fractions. So, hence we can write fractions. If it was just molecules, then we could have not written half of O2 or 15/2 O2, which means half O2 means half moles of O2 is reacting, not half molecules of oxygen is reacting. Second, we had talked about in the last lecture also that this is a extensive quantity, extensive property or extensive quantity. So, the value of this will be written will be as we write the expression. So, if you multiplied this reaction like 2 4 2 4, then this value would be double of what it is, or if you divide by half, then this will be half. So, it is extensive quantity, and this mole is per mole of the reaction what we are talking about. The third thing you must remember that reverse chemical reaction will have opposite sign. So, reverse chemical reaction will have opposite sign, but equal magnitude in del HR. So, the standard reaction heat of reaction or standard enthalpy of reaction for the opposite reaction would be plus 89.4 in this case. If we want to just elaborate with the example, we know this example in decomposition of calcium carbonate solid plus CO2 gas. Now, delta R or heat of reaction for this is 178.3 kilojoule per mole. So, if I write multiply by twice this amount and reverse the reaction, gas twice CaSO3 solid, then delta R for this particular reaction would be reverse. So, minus, and this is twice. So, minus 2 into 178.3, which is minus 356.6 kilojoule per mole. So, these are the three things you must remember. Again one more, that these are stoichiometric coefficient, they represents moles of the reactants and the products. Then delta RH, which is the standard enthalpy of reaction of heat of reaction, is extensive quantity, and reverse chemical reaction will have opposite sign, but of equal magnitude. We will talk about now about the other process, enthalpy change in other process, and we will talk about enthalpy change during phase transition. We all know what is phase transition. Is between transition between different phases of a particular substance. It also sometimes called standard enthalpy of phase transition. And the symbol is, obviously there will be always it is associated with a particular temperature. This is often called latent heat. Often it is called as latent heat. The phase change, example of phase change or phase transition, like solid to liquid. The process is called fusion or melting, and the symbol we will write delta H FUS, fusion, standard at a particular temperature, of course. Liquid to gas, this is vaporization, and the corresponding symbol would be this. Similarly, solid to gas is called sublimation, and corresponding symbol would be this. Now, generally phase transition generally take place at constant phase transition generally happen at different temperature and pressure. For example, water or ice melts at 1 atmospheric pressure at 0 degree centigrade to water, or a water at 100 degree centigrade and 1 atmospheric pressure transition to gas, water vapor. So, we need to mention the temperature at which we are talking about this transition is happening. So, if we write for example, one phase transition example, we can write say H2O liquid to H2O gas. Now, what is the condition? It has to be obviously pure H2O, 1 bar, standard state 1 bar, and if we consider 100 degree centigrade 398 K. Similarly, this is also pure water gas, pure water liquid here, 1 bar pressure 393 K. So, the corresponding reaction enthalpy is found to be 40.66 kilojoule per mole. So, this is the delta H vaporization of water, liquid water at 393 K. So, this example where we are not talking about 25 degree centigrade. So, likewise any heat of reaction or heat of formation also we can define temperature other than 25 degree centigrade. So, you have to calculate, this is 373, sorry, 73. Not 93. We will define, so how we will define, this is a standard enthalpy of vaporization of liquid water. So, we can define standard enthalpy of vaporization is the amount of heat required to vaporize 1 mole, again this is 1 mole of a liquid at a constant temperature and under standard pressure, which is 1 bar. So, sometimes that is why sometimes it is called molar enthalpy of vaporization also, and the symbol we have just mentioned here. Similarly, we can define other standard enthalpy related to the other phase transition. So, like standard enthalpy of fusion, in this case 1 mole of solid is getting transferred to or transformed to liquid at their standard state and that particular temperature. And we also can talk about standard enthalpy. As I said, it could be a heat of fusion or enthalpy of fusion, like that enthalpy of sublimation where a solid is getting transition to a liquid. The magnitude of the transition, you can commonly also, you can instead of vaporize, which you can generalize that delta is transition at particular temperature. You can just write a general form, and the magnitude obviously will depend on the intermolecular forces which binds the molecules together. So, if the intermolecular attraction forces are higher, for example, a delta A vaporization, a standard enthalpy of vaporization of water will be higher than the standard enthalpy of vaporization for acetone, because the interaction attractive interaction force between water molecules are higher because of hydrogen bonding than acetone molecules. Now, we have talked earlier also that delta H is a state function. So, it does not depends, it only depends on initial and final states. So, we can just to we can break any, as I showed earlier also, we can break any reactions is there many number of steps we can possible think of. So, sublimation which is a solid to gas, we can think of as 2-step process, solid to liquid to gas. So, in case of water, we can like solid to H2O gas is your sublimation, with corresponding delta H reaction would be delta H 0. So, we can break into 2 steps. We can write delta H sublimation is equals to fusion plus delta vaporization, that is we can write. Now, this is related to what we many times we are calling that delta H only depends on the initial and final state. So, this is what is the principle behind the Hess's law, which we will now discuss. Hess's law of constant heat summation. Suppose we want to find out with just with the example, it will be clear. So, we want to find out delta F H 0 of at 298 K of ethane gas. So, what is the formation reaction? Constituent elements of ethane is carbon and hydrogen. So, we can write carbon in their reference states. So, graphite plus hydrogen in this reference state to ethane gas standard state at 298 K, and then we can balance it the reaction as per requirement. Now, this reaction is not feasible, graphite reaction react with hydrogen to produce ethane, it is not that common reaction. So, this reaction enthalpy for this particular reaction at 298 K is not experimentally determinable. So, the reaction, though we can imagine this formation reaction, but this is not the way ethane is formed at 298 degrees centigrade. So, for this particular formation reaction, the enthalpy of reaction is not possible to obtain experimentally. So, we have to take an indirect path. So, what is the indirect path we can think about? We can think about that measure the heat of combustion of graphite, hydrogen and ethane, and then using those three reactions we can find out the enthalpy of reaction of this reaction, formation reaction. We will give you example. So, we can write the combustion reaction, which is basically burning in oxygen, and delta R for this reaction at 298 K is 1560. I am not writing kilojoule per mole just to make it faster, but you always should write unit associated with this. I also writing the temperature all the time, minus 393.5, and H2 gas plus half O2 gas gives you H2O liquid, and delta H0 for this reaction is minus 286 kilojoule per mole. This is common for all these things. Now, we can rearrange this equation and multiply with moles, with numbers, because this is extensive quantity, and rearrange to get this equation. We just basically combine these equations to get the this is what our equation we need to get from combining and rearranging this expression. So, if this is my first reaction, this is second, and this is third, what we can do, we can the product is this side. So, we have to reverse this reaction and this is 1 mole. So, you can just reverse these things. In this case product reactant is 3 moles of hydrogen. So, we can multiply 3 with this reaction, and in this case 2 moles of graphite. So, we can multiply it by 2 this reaction. So, what I will do, what we will combine reaction 1 and multiplied by -1, because I am to reverse it, which will give us 2 CO2 gas C2H6 gas plus 7/2 O2 gas, and we have multiplied by -1, and this is a extensive quantity. So, we will multiply the earlier, we have this value, we should multiply by -1. So, we will get 1560 in this case. So, delta H R is 1560. Again I am not writing the units just for our convenience. So, in the second reaction we will multiply by 2 to get to carbon graphite gas, and it will be again twice of the reaction we had. So, it will be twice multiplied by minus 393.5, which we had earlier, and the third reaction we had, we can multiply by number 3, H2 gas plus 3/2 oxygen gas, H2 liquid. We have to multiply by 3 here. So, 3 into minus 286. So, if you can add this, what we will get? This carbon dioxide and this will cancel out. This water, 3 water will cancel out, and 2 oxygen and 3/2 oxygen will cancel out with 7/2 oxygen both sides. So, we will end up as 2C graphite plus 3H2 graph, right side C2H6 gas. So, this is exactly the equation we wanted to get it, our interest. So, this is exactly the expression. So, we can add this number and we can find out the formation reaction, the enthalpy of formation reaction. This will find out to be minus 85 kilojoule per mole, which means delta H formation of ethane gas at 298 K is minus 85 kilojoule. So, this is how what is Hess's law is all about, where you can combine equations to get the reaction, gives reaction enthalpy of reactions which is not practically attainable, which is cannot be determined experimentally. So, as a generic process, we can write if this is my reaction A to B. So, this is the enthalpy of reaction. We can consider intermediate steps. So, this is del H 1, another intermediate H 2, another third step del R H 3, then del H R for the reaction would be del R H 1 del R H 2 plus del R H 3. So, this is the basically this is the general form of the Hess's law. So, we will just take an example numerical problem. If we can focus this problem here, he says that given the standard enthalpy of combustion of graphite is 373, combustion reaction C graphite. So, this is question 10 in our thermodynamics unit. So, graphite is plus oxygen CO2 gas, the reaction is the delta H 0 is minus 393.5. I am not writing the unit one more time, and that of diamond is 395. So, C of diamond, this is combustion reaction gas is 0 is minus 395.4. So, if we add this and reverse this. So, our interest from graphite, so we have to calculate the enthalpy change from graphite to diamond transition. That is the problem is graphite to diamond. So, graphite is a reactants and diamond is a product. So, we will reverse this second equation. So, C graphite, it will to C diamond. So, it will be again the summing up will be to delta for this particular reaction would be minus 393.5 and reverse, which will add the reverse one. So, basically 395.4, which will turn out to be 1.90 kilojoule per mole. So, this is the example how you can the example of Hess's law what we are applying, and this reaction which we are talking about all the time is a combustion reaction, and so we can also define a heat of reaction or enthalpy of okay, we will talk about that in the next class, where we will talk about enthalpy of various types of processes, different types of processes or reactions. So, that will be from where we will start, and one of the example would be the combustion reaction we just talked about. So, we will stop now, and we will start about the enthalpy of different types of standard enthalpy of different type of process in next class.